we need to talk about chemical reactions. So chemical reactions are chemical changes, a description of a chemical change. In a chemical reaction, we have one or more substances that are changed into one or more new different substances. What we have going on here is just the rearrangement of the atoms. The atoms themselves are unchanged. A combustion reaction is a specific kind of chemical reaction where a substance that has a substance is reacting with oxygen and is forming one or more oxygen-containing compounds. These reactions typically release a lot of energy, and thus they are useful in meeting our energy needs. So a chemical equation is just a shorthand way of describing a chemical reaction instead of using a lot of words. The basic form is on the left are the reactants, on the right are the products, and there's an arrow pointing, and so we start over here, and what we start with here changes and becomes this. So we say the reactants react to produce the products. There's a lot of information about a reaction in an equation. We'll have the formulas of the reactants and the products. We'll have their physical states. These are called state symbols, the abbreviations for the different states of matter. So G if it's a gas, L if it's a liquid, S for solid, and AQ for aqueous, meaning it's dissolved in water. A lot of things are aqueous. We can also see the relative numbers of reactant and product molecules from this chemical equation, and we can use the equation to determine the mass of reactants used or the mass of products produced. So here's a very simple combustion reaction, methane. Methane is a main part of natural gas. And so when methane gas burns, it produces carbon dioxide gas and water in the gas state. So here we can describe it like this: CH4G, formula for methane, reacting with oxygen. Oxygen is a gas. We write the formula O2 because oxygen is one of the diatomic elements, and so its formula will be O2. And that's going to produce carbon dioxide gas and water vapor. The reason that water is in the gas state here is because these reactions release a lot of energy, and so they are hot, right? If you think about a Bunsen burner, it's combusting methane. The water that gets produced is going to be at an elevated temperature, so it will be in the gas state. So the chemical equation is supposed to describe the rearrangement of the atoms. But we have a problem here because this reaction or equation is showing that we have 2 oxygen atoms over here, but over here there's 2 and another one, there's 3 oxygen atoms. And so just like building with Lego bricks, you can't just suddenly have a new red 2x2 brick appear, right? Sometimes that would be really convenient, but you can't do it, right? You can only use what you had to start out with. We also have a problem with the hydrogens. There's 4 hydrogens over here, and now there's only 2 hydrogens. So 2 of the hydrogens disappeared? That's not possible. The law of conservation of mass says that the mass of the products has to be equal to the mass of the reactants. So there's something wrong with our equation. So what we need to do is balance the equation. We're not going to change the chemical formulas because those are correct. What we're going to do is we're going to change how many of those we have. So those are called the coefficients. So we're going to put numbers in front of the chemical formulas. Those are called coefficients. These numbers within the formulas, the subscripts, do not change when we balance an equation. So what we're going to do is we're going to adjust the number of molecules so that we get the same number of each kind of atom on each side. And here we have this illustrated with the ball space filling models. And so here we see methane has this one black, that's the carbon, and 4 whites for the hydrogen. Over here, carbon dioxide is a black one with 2 reds for the oxygens. So in the unbalanced equation, this is what we had if we have it without the 2's. And so there's 1 black ball here and 1 black ball there, but 4 white ones here and only 2 there. That can't happen. So if we start with 4, we must end up with 4. This is the only thing that has hydrogen in it, so we must need another water molecule. So now we are using all 4 of those white spheres. Over here we have 2 red spheres. On this side we now have 1, 2, 3, 4. So that means we need 2 of these so that we have the same number. So think of these like a child's toy. You can take these apart and put them back together. You can rearrange them. Do you see how you can take these pieces and make those things instead? That's all we're doing in a chemical reaction. We don't usually use pictures like this, but you can train your brain so that when you look at CH4, you can imagine, oh, well, that's a carbon ball and 4 hydrogen balls. You can make them whatever color you want, but we're just pulling these atoms apart and sticking them back together in a chemical reaction. So we need to be able to count how many atoms are in a chemical equation so that we can balance. So this is asking us how many oxygen atoms on the right-hand side. So this is the right-hand side, the product side, and they want to know how many oxygen atoms are there. So if we look at this compound, in 1 unit of that compound, how many oxygens are there? There's 3. And the number 2 is telling me I have 2 of those things, right? So that's 2 times 3 oxygens. Over here, in this guy, CO2, each unit has 2 oxygens. Kind of like a bicycle has 2 wheels, right? And this is saying I have 4 bicycles. 4 bicycles means 8 wheels, right? 4 times 2. It's not hard, it's just so different from what we're used to thinking about that it takes a while to get used to. But this would be 6 oxygens and 8 oxygens, so a total of 14. Any questions? Killing myself in the mask here. Bad thing about having dogs?
Just find fur everywhere.
Yeah. There's dog hair everywhere except on the dog.
I have a Maine Coon now, and they're like the huskies of the cat world.
Yeah. I'm not trying to do dictation here, thank you. Any questions? So there are different ways to balance chemical equations, and there's not necessarily one that's better or one that works the best all the time. So this is a general approach. I urge you to give it a try. If you come up with a better way, that's fine. So the general approach here is to write a skeletal equation. So that means figure out the formulas of your reactants and the formulas of your products and write those down. Then we start balancing the equation. In general, it's a good idea to balance things that are in more complicated substances first. and leave anything that's a pure element to the end. Balance anything that occurs as a free element last. Depending on how you go about this, you can end up with coefficients that are fractions. So when we have it balanced, we need to clear the fractions by multiplying by the denominator. And then you always want to check and make sure that your balancing is correct. So we'll do some examples. We'll also get a little practice with nomenclature here. Write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. So first step is we need the chemical formulas for these substances. So we have solid silicon dioxide, solid carbon, solid silicon carbide, and carbon monoxide gas. The word "and" is like the plus sign in the equation, and to produce is like the arrow. So silicon dioxide, what kind of a compound is that? Ionic, molecular, or acid? What kind of element is silicon? Silicon is on the non-metal side of our stair-step line. It's a non-metal, so this is not ionic. That means we're going to use this prefix to tell us how many oxygens. So I've got silicon, and I've got 2 oxygens, because it says dioxide. It tells me this is a solid, so I'm going to put an S in parentheses to indicate that. And then I'm going to go for the next one. I'm going to leave a space here because I'm probably going to have to write a number in there. Solid silicon carbide. Well, we already established silicon is a nonmetal. So this is another molecular compound. It's not a metal. So there's silicon, and carbide would refer to carbon, right? There aren't any prefixes there. Yeah, question? No. Oh, yes. Yes. Thank you. I don't necessarily do very well on cold medicine, so thank you very much. Yeah, my bad. That belongs over there. Well, let's finish with him since we started. There aren't any prefixes here. So if there's no indication of a number, then we usually assume that it's 1. So it's just 1 silicon and 1 carbon. It used to be fun. I could ask Siri and what the formula for silicon carbide was, and she'd say it was sick, because she'd pronounce that. She doesn't do that anymore. It's kind of disappointing. That's a solid. Okay, back to where we were supposed to be. Solid carbon. So carbon's an element. Is it a diatomic element? No. So we don't need to write a 2, we just write C. And S for solid, and our arrow. Carbon monoxide. Is that a molecular compound? Yeah, because carbon is not a metal. So carbon monoxide, we've got carbon monoxide, 1 oxygen. That's a capital O. And that's a gas.
Monoxide or monoxide?
Yes. You can pronounce it monoxide or monoxide. Tomato, tomato. Okay, so that's our skeleton. That's the important first step. Good news, on an exam where I'm asking you to balance equations, I'll give you those. Okay, I'm not going to make you write all the formulas as well. But homework or worksheets, you might have to do that. So now what we want to do is, and one way to describe this is balancing by inspection. We're just going to look at it. So we have nothing terribly complicated here, but here we have a silicon with 2 oxygens, and there's a silicon with a carbon and a carbon with an oxygen. Here we have carbon all by itself. So I want to leave that one for the end, because if I change the coefficient on this, it doesn't mess up anything else. If I change the coefficient on SiC, then it also affects the silicon. A lot of times you can just start with the first element and work your way through. So let's try that. So over here on this side, there's only 1 silicon atom. Does that make sense? And on this side, how many silicon atoms? 1. They are equal, they are balanced, like a teeter-totter. There's 1 on each side, it's balanced. We don't need to do anything. Let's look at the oxygen. How many oxygens are here? 2. How many oxygens on this side? Only 1. We can't take anything away, but we can add more. So if I say there's 2 carbon monoxide molecules, now I'm going to have 2 oxygens. That changed the carbon, but we haven't messed with the carbon yet, so we're okay. Everybody following? When you see how it works, it's actually simple. But you actually have to see how it works first, and that's the hard part.
I actually love balancing.
You love balancing equations? Some
I like
people
when there's
do.
the huge ones of like 8 or 9 different.
Yeah, it can be fun. So now I've got 1 carbon over here, and here I have carbon in both of these compounds, so we need to make sure that we consider both of them. This one has just 1 carbon atom, and here I have how many carbon atoms? 2. So there's a total of 3 carbon atoms on the right side. I need 3 carbon atoms on the left side, so I'm going to put a 3 in front of the carbon. Now, if we check, we can see there's 1 silicon, 2 oxygens, 2 oxygens, 2 plus 1, 3 carbons, 3 carbons. That's checking. Okay? Any questions? Let's do another one. Write a balanced equation for the combustion of gaseous ethane, a minority component of natural gas, in which it combines with gaseous oxygen to form gaseous carbon dioxide and gaseous water. So again, I'm just going to highlight the different reactants and products. And then I see I have ethane combines with oxygen, so it's ethane plus the oxygen to form, there's my reaction arrow, carbon dioxide and water. Well, the first one is easy because you just learned about things like ethane and methane, right? And so they're not really expecting you to just hammer out that formula yet. Ethane is C2H6. And we're told what the state is, so we should write that down. Gaseous oxygen. Now, that needs to be O2 because oxygen is one of the diatomic elements. When a diatomic element is present alone, not with carbon or hydrogen or something else, they always use the buddy system, and there's always going to be 2 of them. Right, so that's O2. To form, we have carbon dioxide. So that's like carbon monoxide, but there's 2 oxygens. And we're told that that's a gas. And gaseous water. What's the formula for water? H2O. Okay? Well, let's try just starting at the beginning here with the carbon. I have 2 carbons, right? And over here, there's carbon in this one. There's only one of them. So if I write a 2 in front of that, then that'll give me 2 carbons on the right side, 2 carbons on the left side. There are 6 hydrogens. Over here, I have 2 hydrogens. What do I need to multiply that by to get 6? It's 3, right? 2 times 3 is 6. So now we have 2 oxygens here. We can change this coefficient and it's not going to mess anything up. So what we're going to do is we're going to go and see what's over here so we can tell what should be here. So in this one, 2 CO2s, I have 4 oxygens. And in 3 water molecules, I have 3 oxygens. So that gives me a total of 7. What do I have to multiply 2 by to get 7? You can't use a whole number there. You could use 7 halves, right? Because 7 halves times 2 is 7. That's how you can end up with a fraction as a coefficient. Most students would rather avoid fractions whenever possible, right? So let's not do that. So these oxygens are coming in pairs, and this is an odd number. I call this the odd-even problem. If this was an even number like 8, it'd be easy, but it's not. We can change an odd number into an even number by multiplying by 2. So what I'm going to do is I'm going to multiply by 2, and I'm going to multiply by 2 all the things that I've already balanced. So this 2 is going to become a 4. This 3 is going to become a 6. What's the coefficient here right now? It's a 1. I'm going to multiply that by 2 also. Because I did it everywhere, I have not messed up the carbon and hydrogen balance. Now I have 4 carbons and 4 carbons. I have 12 hydrogens, and 6 times 2, 12 hydrogens. Now I have 8 oxygens in the carbon dioxide and 6 oxygens in the water, and that adds up to 14, which is a conveniently even number. So if these are coming in pairs, I need 7 pairs to get 14 shoes, or 14 mittens, or 14 oxygen atoms. So 7. Any questions? This is one of those things that you can watch someone do it and follow along, and you're like, oh yeah, I see how that works. But then when you try to do it yourself or explain it to someone else, you realize, oh, I don't quite have that down yet. And that's why we need some practicing. Here's another one. This is one that has ionic compounds in it with polyatomic ions. Write a balanced equation for the reaction between aqueous lead-2 nitrate and aqueous potassium chloride to form solid lead-2 chloride and aqueous potassium nitrate. Okay, so that kind of helps us to see where things are going to be. These are ionic compounds now, lead-2 and nitrate. So we need the formulas for those ions. Lead is Pb, and the Roman numeral is telling us what the charge is. What's the formula for nitrate ion? NO3, the -1 charge. Why? Because they decided it was, and we memorized it, right? So to combine these two so that I get a neutral compound, this is a +2 charge and a -1 charge, I need two of those guys, right? If I had two nitrates, I'd have a total of -2 charge and +2 charge, and those add up to 0. So the formula for that is Pb NO3 2. This ion has more than one atom in it, and so to avoid being confusing, we need to put shrink wrap parentheses around our bundle and put the number of bundles outside. So there's two of these combinations. And we were told that this was aqueous. Any questions? So the next thing is potassium chloride. What's the formula for potassium ion? Potassium is in group 1A. Group 1A make +1 ions. Chlorine is from chloride, right? And what charge does chloride have? -1. So look at the periodic table and we count from the noble gases being 0, we count backwards negative, -1. So +1, -1, we can just put those guys together and they will be neutral. And it also says that's aqueous. So now we need lead-2 chloride. Well, we already have our ions here. That's lead-2. And this is chloride. So what's the formula for that going to be? Oh, it didn't. There we go, sorry. I need two of those, right? To make the charge. So that's going to be PbCl2. And it says that's a solid. This is a single atom. It doesn't need parentheses. If you put parentheses, it may look stupid, but technically it's not wrong. And as is often the case, I did not center this very well, so I'm going to move it over. The last one is potassium and nitrate. Whoops. So potassium ion. Let's see if I can get just one of those. And nitrate ion. I look at the charges to determine the formula. +1 and -1. I don't need to do anything fancy. I just need one of each. And that's aqueous. So I need to balance this. Over here, I've got one lead ion, right? And over on this side, how many lead ions do I have? On the right side? 1. So that one's okay. Here, I moved one of those guys, so I have to replace it. I have 2 nitrate ions. Over here, how many nitrate ions do I have? Just 1. I could balance the nitrogen and the oxygen separately, But in a reaction like this, the NO3 stays together, so I can save a little time in thinking by just keeping it together and balancing it as a bundle, right? So I've got 2 of them over here. That means I need 2 of them over here. Well, if I get another nitrate ion, that's also going to give me another potassium ion if I have 2 of those. Any questions? How many potassiums on this side? Just this one, right? K plus and Cl minus. Over here, now, because I was balancing the nitrate, now I have 2 potassiums. So to get 2 potassiums on the other side, I need 2 of the KCl's, which is going to give me another K plus and another Cl minus. And then the last element, lead, nitrate, potassium chloride. So here's chlorine, and I've got 2 of those. I've kind of drawn it out down here, but I've got 2 chlorines. And how many do I have over here? Also 2. So that one's fine. Sometimes when you're balancing an equation, you get to this point and the Cl2 is not fine, and you find yourself having to change that, and then you're like, and that's going to mess up everything else. I'm going to be going in circles forever. That's the time you need to start over, okay? Double check your chemical formulas. If I had this formula wrong, if I had PbCl instead of PbCl2, it would be impossible to balance the equation. So if it's looking impossible, double check that you've got the correct formulas. Try it again, okay?